Alright, so this is just going to be a little review video over some basic waves. So some of the things that we have discussed is, just some of the terminology. You have frequency, which is cycles per second. We have period, which is seconds per cycle. So that lends you to see that frequency is 1 over period. Period is then 1 over frequency. I think some of the reviews that we've done in class, I think you have that concept pretty well. Some of the other things that we have discussed are crests and troughs in terms of what a wave looks like. A crest is the very top. A trough is the very bottom of a transverse wave. Both of them can be considered amplitudes. Uh, Amplitude is just maximum displacement away from the 0 point or equilibrium. And you know that amplitude is what is kind of tied into the energy of the wave, not necessarily the frequency or the wavelength or anything like that, but more of the amplitude. We have discussed a little activity that we did with refraction. So if a wave is coming in at an angle with respect to the normal, right, and it's going from something that is low density to high density, which means maybe this is a sound wave, and we go from something that is slow to fast, right, low density to high density, then it's possible that it's able to speed up as it comes in. And if it's able to speed up, it bends away from the normal. If it is the opposite way, and it comes in and it goes to a particular medium that is slower, so from high velocity to slow velocity, then it will bend towards the normal. And this just has to do with speed changes, right? When the speed changes from slow to high or high to slow, then it bends, and we did that activity outside. Um, what else? What else have we talked about? We have discussed a whole equation of velocity is equal to wavelength times frequency. So if we have something that says the wavelength is, I don't know, 20 centimeters, and the frequency is 10 hertz, then first of all, we know that we don't work in centimeters, so this would have to be converted to 0.2 meters. Then the speed of the wave would be equal to 0.2 meters, which is the wavelength, times the frequency of 10 hertz, which of course gives us 2 meters per second. Now, what if I didn't give you frequency? What if I said that the period of it is, I don't know, we'll say 4 seconds. I gave you a wavelength and I gave you a period. Then it's you would have to have one extra step in there saying, oh, frequency is just 1 over period, which is 1 over 0.4, or 1 over 4, excuse me, which gives a frequency of 0.25 hertz, and the whole thing would just change in that respect. This would become 0.25, and then this would obviously become something like what, 0.05, something like that. I'm just doing that off the top of my head. I don't even know if that's right, so you have to check me on that one. Then we've also seen some things where the speed of the wave can be affected by other things. Like in a slinky, we noticed that the tension of the wave can affect it. If there's more tension, then the speed of the wave actually increases. And then we have this weird thing here, which is known as the mass density or linear density. So this mu is equal to mass divided by length. So if it's a heavier string or a more dense string, it has a higher mass for any given length, that's going to slow you down. But if it's under a great tension, then the tension might be able to speed you up. So this is just qualitatively knowing what goes into the speed of the wave. You'll be tested over that. There might be a bonus question over that particular formula on the test. Then we discussed standing waves. So if we discussed mainly standing waves on a string or a slinky, then we notice that the fundamental looks like something that can be drawn like this. And we notice that whatever length of string that this is doing this on, this is only half a wavelength. So if the length of the string is saying 1 meter, then the wavelength itself is actually 2 meters. Okay, this is wavelength. So whatever the length of the string is, you have to actually multiply by 2 in order to get the wavelength. Vice versa, if you're given the wavelength of the string and you know it's a fundamental frequency, then you divide it by 2 in order to get the length of the string, if that is what you're asked for. I don't know why I can't extend my view. Anyway, so if that is the fundamental, then we know that we can just carry it on for each harmonic. So this is the fundamental, or the first harmonic. This is the second harmonic. And this would be the third, and so forth and so forth. So this is the third harmonic. Now, let's say that this is, I don't know, 20 hertz. Then each harmonic above it is actually the harmonic number multiplied by what the frequency is. It's an integer multiple. So this is 40 hertz. This is 60 hertz. And it just keeps on going and going and going. Notice how the wavelength changes for a given length of the string. This is 2L. If L is the length of the string, then wavelength is equal to 2L. Here the wavelength is just equal to L. And here the wavelength is actually equal to 2/3 L. If you envision this as being chunked up into threes, then 2/3 of it is an L. What do you need for a wavelength? You need an antinode. You need actually two antinodes, right? These points here where that go back and forth, that's an antinode. Here, that is a node. So if you have two antinodes, then you have a wavelength. For every two antinodes, you have a wavelength. So if you had something that was like the eighth harmonic, let's see if I can draw that. 2, 3. Ooh. Yeah, let's see. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8 harmonics. I know that's a little messy, but how many wavelengths do we have here? We have 1 wavelength, 2 wavelengths, 3 wavelengths, and 4 wavelengths. So you can take the eighth harmonic, or 8, and divide it by 2 and give you how many wavelengths you have. And that is showing you that, say, like the wavelength here is actually 2/8 L, or it can also be equal to 1/4 L. Okay, pattern like that is going to become really important as we move into the next unit. But you notice how the wavelength is actually getting shorter and shorter and shorter as the frequency gets higher and higher and higher. The frequency here would actually be 8 times 20, which is 160 hertz. Okay, so in terms of the test, all of this is prime stuff that's going to be on the test. You just need to remember that what is it that you need. If you don't have what you need, how can you get it? It's all about problem solving. Many of you say that the tests are always harder than the homework, and that's just because I end up adding either one or two more steps. So you just need to think, what is the equation that you need, and what is it? What are the numbers? What are the concepts? What are the things that you need to be able to calculate the answer? And if you aren't given those outright, how is it that you're able to calculate those in particular? So it's just problem solving, taking it one step at a time. Okay, good luck tomorrow.